do the beginning of the universe, a cup of tea, and a high energy collision of gold nuclei all have in common? The answer may sound fantastically hyperbolic, but it is quite literally the truth. That answer is hydrodynamics, and is one of the most ubiquitous and powerful theories in physics, and in my opinion, one of the coolest. Hydrodynamics is a theoretical cornerstone of an ongoing effort to understand the results of an ongoing experiment at RHIC, the relativistic heavy ion collider. Heavy ion because they take gold atoms and strip them of their negatively charged electrons, leaving a collection of protons and neutrons, or in other words, a positively charged nucleus. Relativistic as in Einstein's relativity. That is, those nuclei are accelerated to speeds so fast, they're comparable to the speed of light. And collider because then we, smash them together at those speeds. Then, like water expanding to fill its container, the matter produced in the aftermath of the collision expands until it hits the walls of our detector. However, unlike water, this system is so hot and dense initially, 100 million times hotter than our sun, in fact, that the protons and neutrons melt into an exotic phase of matter called the quark-gluon plasma. This recreates conditions that our universe experienced up to microseconds after the Big Bang, albeit on a much smaller scale. If you were to scale up our detector to the size of the Earth, the system that we're interested in would be 1,000 times smaller than the width of a human hair. This makes our task all the more challenging. For water, when you know its temperature and its density, you know exactly whether it's behaving as a solid, a liquid, or a gas, and you know exactly how it transitions between the three. This is not the case for the quark-gluon plasma, and we know almost none of these properties with certainty. However, we do have theoretical reason to believe that the quark-gluon plasma possesses a phase transition mathematically identical to the liquid-gas phase transition, water. I am part of a large-scale theoretical collaboration that aims to model the behavior of this exotic nuclear matter in the hopes of discovering experimental evidence for exactly this transition. Hydrodynamics has a pivotal role in this. Implementing the hydrodynamic code correctly in conjunction with the rest of the model is a large-scale task that requires collaboration from many different areas of physics. Our problem is exacerbated by the novel nature of hydrodynamics in the relativistic regime. Our field is literally developing and deriving much of the physical theory from scratch. When my group members and I are finished implementing the hydrodynamic code correctly along with the rest of the model, we'll be that much closer to understanding and answering some of the most fundamental questions about the universe, while at the same time helping to develop a physical theory that would make Einstein himself proud. So the next time you're boiling your water for tea, take a moment to appreciate the graceful way in which nature hides her complexities and at the same time constructs beautiful, simplistic, and far-reaching connections. Thanks.